Hello guys, hope you are doing okay and hope this video finds you well. I just wanted to go through some revision of principles, that is the end of term that we did, the term 3 2024. At least I want just to go through the section A, then there will be another tutorial for section B. So if we start with the first question, which said state the following laws as used in network theorems in electrical principles. So one was Kirchhoff's current law, the other was superposition theorem, the next Norton's theorem. So if you look at those three theorems, they come from the topic 2 of electrical principles after introduction. So after introduction, we're introduced to the circuits, the components of a circuit, the series and parallel. After you know how to do the calculations of a series and parallel circuit, then there is the application part where you can apply the three laws in order to solve complex circuits, that is those that have more than one source of EMF, that is or potential difference. So when asked about Kirchhoff's current law, all that has to come into your mind is we are talking about current at a node or a junction, and the relationship between those currents is depends on the direction, that is currents that move towards the junction and also current that moves away from the junction. So putting it in statement form, you can say it states that in any junction, in an electrical circuit, the total current flowing towards the junction is equal to the total current flowing away from the junction. Alternatively, you can use the algebraic form in the mathematical way, where you say the algebraic sum of currents at a junction equals to 0. So that one, you'll have already stated the Kirchhoff's current law. The next, superposition theorem. So this one talks of a linear network or a linear circuit. A linear network or a circuit it's a circuit or a type of circuit that consists of one or more sources of EMF, and we have some parameters in it. It can be resistors, it can be inductors, it can be capacitors. So depending on how the circuit is, but if it has more than one source of EMF or voltage source, then it's called a linear circuit. So we look at calculating the resultant current that is flowing in that circuit based on the relationship between one source of EMF and the other one is replaced by a resistance that is equal to the internal resistance of the circuit. So it states that any linear network with more than one source of EMF, the resultant current flowing in any branch is the algebraic sum of currents that will be produced by each source acting alone, with all other sources being replaced by resistances equal to the internal resistances. So if you are not able to state it correctly, I always advise you to use a circuit. You can use a circuit that has two or more sources of EMF. You can label the currents in each branch. Then you can state how we solve the currents for each branch. So if you always look at most of the calculations that we did in class, we were using current 1, current 2, current 3. So that is the resultant current that is flowing in each branch. But in order to get that, we'll have to consider one source of EMF as we short the other by replacing it with another resistance. Then we go to the other source, that is B, as we short the first source of EMF. So that's how we calculate, that is how we relate the superposition theorem. Then we have the Norton's theorem. It says that the current across in any branch of a network is the same as that which will flow if it were connected across a source of electrical energy. The short circuit current of it is equal to that which will flow in the circuit, and the internal impedance is equal to the internal impedance across the open circuited branch. So we are talking about a linear circuit, and if you looked at also the calculations of Norton's theorem, we are talking of a linear circuit and a resistor. So instead of calculating current in each branch, we can consider that linear circuit by confining. We confine all those components or the resistors into one, which is in series with the load resistor. That is the resistor that we are required to find the current that is flowing towards it, and also the voltage drop, because for a series circuit, the voltage drop is different, the current is the same. So that is just how you apply when you're asked about the laws, that is from the network theorems. So if we go to the next question, was differentiate between charge and force. So this type of question is not something that it inahitaji a lot of thinking. So you can just use a table format whereby you put charge and force. We always denote charge by capital Q or small q. Then you always denote force by capital F. That is a difference because when you're calculating, it shows which quantity you're working on, which variable. When you can use the SI units where charge is measured in coulombs, then force is measured in newtons. Then you can use the variations, that is a scalar quantity. A scalar quantity is either we look at in terms of polarity, that is positive and negative. Then force is a vector quantity because it has magnitude and direction. If you look at those calculations, you see that they say that a mass is moved vertically or horizontally towards the Earth's surface. So telling you that there is a direction and at the same time there is a magnitude. Then it exists inherently in particles like electrons and protons, then arises due to the interaction between charges, electrical field or magnetic field. So that is how we differentiate. So if you're asked any questions about differentiate comparison, never use the negative words like not. Always use significant features of that particular item. If you say it is measured in newtons, so in order to differentiate that, you cannot say it's not measured in newtons. So what is it measured in? So that is how we contrast to bring that difference. So that one is also how you can answer some questions on differentiation or contrasting. Then you can go to the next question. Define a transformer as used in electrical machines. We studied during the previous class, we went through the transformers. We discussed about the parts of a transformer. We also discussed the ways in which a transformer can either be a step up or a step down. So in order to define a transformer, you can use an option of using the parts of a transformer to define it. Or also you can use the conversion of electricity or energy from one source to another. Someone can also use the stepping up or stepping down perspective. So depending on how you put it, is okay. So from my own definition, it is an electrical device that transfers AC energy between circuits by electromagnetic induction. It changes voltage levels by either stepping up or down while maintaining the same frequency. Its main parts are primary and secondary winding and a magnetic core. So if you look at that, I've defined what is a transformer. First, I've looked at the conversion of energy from one form to another. Then the interaction. In order to be a step up or step down, there is that mutual interaction. It's called an electromagnetic induction. Then there is a stepping up or stepping down depending on the connection of the transformer. Then I also include the aspect of the parts. In the previous class, we learned about the parts. We had the primary winding, we had the secondary winding, and we had a magnetic core. For our case at class, it was a ferromagnetic core. So depending on whichever transformer it is, depending on the materials that are made up of it, then you can also define that, the definition of a transformer. So next, you go to list 4 electrical instruments with the quantities they measure. So in electronics and in your entire course, I'm very sure that you interact with a lot of materials, a lot of instruments that measure different parameters in the electrical sequence. So we have the ammeter. We have that analog ammeter that measures current. We have the voltmeter that measures voltage, ohmmeter resistance, wattmeter power, energy meter energy. The multimeter measures voltage, current, and resistance at the same time. Frequency meter, it measures frequency signals in terms of waveforms. So as you advance, you'll be able to know what a frequency meter is. Capacitance meter for capacitor. Oscilloscope, it measures waveforms. Then we have the inductance meter, which measures inductance. So that question was just trying to make you to recall, now that you go through practicals on a lot of units that are related in the electrical field. What are some of the units, the instruments that you can use to measure something when performing a practical or when conducting an installation, whichever activity that it might require. So it's called a recall question. And next we have an ideal, that is a calculation. An ideal transformer has a turns ratio of 2:7 and is fed to a 240 volt supply. Determine its output voltage. So if you ask some questions like this, I always encourage, the same time nilikuwa pale class, I always encourage you to always write the initial formula, those formulas that are used to emphasize most of the time. So if you look at there, we have been given a turns ratio in number of turns in ratio form. So if it's 2:7, then it means it's 2 turns in the primary winding. Then we have 7 turns in the secondary windings. Then it's fed to a 240 volt supply being fed to, which means that 240 is the input voltage. So you have to determine the output voltage. So there is that initial formula that I was saying, N1 over N2 is equals to V2 over V1, which is equals to current I1 over I2. So the current was inverse. So if you look at that was the initial formula. Now we narrow down to the question where we have been given the turns ratio and the voltage. So you can now relate the turns ratio and the voltage. That is denoting the N1, N2. N1 representing the number of turns in the primary, N2 representing the number of turns in the secondary, then V1 representing the input voltage. Because of the question, it's fed to a 40, being fed to a 240 volt supply. There is the input voltage. So it's N1 over N2 is equals to V1 over V2, making V2 the subject. Find it is 840 volts. So according to the knowledge that you understand about transformers, if the input voltage is 240 and the output voltage is 840, then it means that it's a step up transformers. It's stepping up the voltage from that low voltage of 240 to a high voltage of 840 volts. Then next we have step 3, possible faults in induction motors. We learned of induction motors. So we learned of some of the parts of an induction motor. So if you look at a fault, since we said that all machines or equipments are not 100% efficient, we have that 99% efficiency. So that 1% is what contributes to faults in any electrical circuit, electrical machine or device. So one can be the stator faults. Stator faults can be as a result of the windings inside the motor might have short-circuited and come into contact with the casing, the outer casing. If it comes into contact with the outer casing, then it can cause an open circuit or a short circuit or a ground fault. Then we have the rotor faults. The rotor faults also can occur as a result of those segments inside might have a short circuit. The coils inside might also short circuit and come into contact with the rotor segments, and at the same time they can come into contact with the stator. So that one can cause a fault. Then you have an unbalanced supply voltage. If the voltage is always not constant, it always keeps on fluctuating, then it means the revolutions per minute will always be fluctuating. And depending on the load that you're driving, remember the motor has to drive a load. And if that load requires a stable or a constant supply voltage, those fluctuations in input voltages can cause a fault in that motor. So that's also another fault. Then you have single phasing. Remember the last time we talked about a three phase. A three phase, if you now make that motor to become a single phase, you are now making it bad to look like it's not meant for that purpose. So if you single phase, then it means we have 2 extra phases that are lying just dormant. So you need to make sure that you utilize the 3 phases so that you can balance the load. the load can run in a balanced move. Then you have over voltages. Over voltage can be as a result of from the main supply due to maybe a fault in the regulator. It can cause an overvoltage which can exceed the ratings of the load, because if it exceeds the rating of the load, then the motor will have to get burnt. Then you have the harmonics. Harmonics, these are just they come as a result of friction due to the interaction of the stationary part and the revolutionary part of the motor, especially the metallic part. They can cause the frictions which can create some harmonics, and in turn, with time, it can create a fault. So those are some of the possible faults that can occur in an induction motor. So next we go to complete the table below with the correct quantities and the SI units. This is just a recall question from the introduction part. Basic electrical quantities, electrical principles. There is a quantity, SI unit, and a symbol. So current, it is measured in amperes. The symbol is A. So you look at the spellings, amperes. There were some guys who are writing amperes in French. I don't know the correct spellings. Then you have mass, kilogram, kg. Power, it's watts, capital W. So there were people who are writing power is measured in joules. Joules, it's energy. Energy is measured in joules. So joules is denoted by capital J. So this is just a question that recalls you on the previous introduction topic. Then we have the next question, which was with the aid of sketches, show the following connections, star and delta connections. So this is the last bit of the part that we did on three-phase systems, whereby we said a three-phase system can either be connected in star and can also be connected in delta. So for star connections, we said that all the loads are connected at a central position, which is a node, and then the outer endings from the load are now connected to the mains. If you look at the star connection, the loads are connected to a common node. Then the ends of the load are connected to the mains. That is the red phase, the yellow phase, and the blue phase, RYB. Then for a delta connection, we said that all the loads are connected in a ring, and the outer ends of the loads are connected to the faces. So if you look at there is a triangle with 3 loads connected in form of a ring, and then the outer endings are now connected to the main supply. So that is how you can show the connections of a delta, and at the same time you can show the connections of a star. So next we go to the next question, which was a 6-pole generator has a lap wound armature with 40 slots with 20 conductors per slot. The flux per pole is 25 milliweber. Calculate the speed at which the machine must be driven to generate an EMF of 300 volts. So like I always say, if you are given any calculations, you always refer yourself back to the initial formula that I gave in class. So I said, when we are doing the structure of the armature, the action of the armature and the commutator, then we did some calculations. So I said that the generated EMF is equals to 2P phi NZ divided by C. 2P represents the number of poles per pair. And I said if it's a 6-pole, then it means we'll have to divide 6 by 2 to get the number of poles. That knowledge is applied when dealing with there's a calculations there that we deal with slip for 3-phase induction motors. So always remember that P represents the number of pairs per pole. Then phi is the flux per pole. N represents the speed in revolutions per second, not per minute, but it's per second. Then Z represents the number of conductors. Then you're dividing by C. So if you write the initial formula as E is equals to 2P phi and Z divided by C, but you'll have to remember that the structure of the armature is either in 2 ways. We have the lap wound and the rotor wound. So for the lap wound, we always say C is equals to 2P for a lap wound. So we'll equate that 2P where there is C. So it will be E is equals to 2P phi and Z divided by 2P. So the 2P's will cancel each other. E is equals to phi n z. So from the questions we are given as the generated EMF 300 volts, the phi is 25 milliweber, that is 25 times 10 raised to power negative 3, or 25 divided by 1000. Then the Z, the number of conductors per pole. So if you look at the question, there is a number of slots and the number of conductors. So it means that in each slot, for one slot, there are 20 conductors, but there are 40 of them. So it would be 40 by 20 to find the value of Z, the number of conductors. So it will be 40 by 20 will be 800. So the generated E is equals to phi n Z, because the two p's cancelled each other. So you can now decide to make n, which stands for the speed, the subject. So if you make n the subject, it will be E divided by phi times Z. So the E will be 300 divided by 25 times 10 raised to power negative 3. Then multiplied by 800, you get 15 revolutions per second, which converted to RPM, or revolutions per minute, it will be 15 times 60, which is equivalent to 900 revolutions per minute. So for your case, you can just leave it at 15 revolutions per second, unless otherwise the question asks you to now convert it to revolutions per minute. So that's how the calculations can be done. Then next we go to another calculation. A current of 3 amperes in a conductor of PD 240 volts through cables of resistances 100 milliohms if the field winding resistance is 50 ohms and the armature resistance is 40 ohms. Determine the terminal voltage and the EMF generated in the armature. So always remember the initial formula that I gave. The terminal voltage V is equals to E, that is the generated EMF, minus armature current times armature resistance. And if you look at the armature current times armature resistance, is a type of loss. When we are doing the losses found in three-phase systems, we learned of copper losses, friction and windage, iron losses, the I squared R. That's where we derive the armature current times the resistance, armature resistance. So from Ohm's law, and for easier clarification or clarity, you always draw the diagram. So for me, I drew a diagram whereby I showed the load which has power there. Then you have the resistor, that is 100 milliohms. You have the field winding, you have the armature resistance that is in parallel with the field winding. So determining the generated EMF from Ohm's law, current is equal to voltage times current over resistance. And we have another formula for power, because the load had some power. So current will be equal to power divided by voltage, from P is equals to VI. Power is equals to voltage times current. We have power and we have voltage. So you have to determine the supply current. So current will be equal to power divided by voltage, that is 40 times 10 raised to power 3 divided by 200. You get 200 amperes. Then the field current is a formula that we calculated in class. Field current is equals to the voltage at the terminal divided by the resistance of the field winding. That is 200 divided by 50, you get 4 amperes. Then there's another formula. Now that we have the field current and we have the supply current, we can also have another armature current. That is the current that is coming as a result, or the source is from the armature resistance. So that direction. So you can use Kirchhoff's current law to relate the two, whereby if you want to get the armature current, will be equal to the field current plus the initial supply current, which is 200 plus 4. It will be equivalent to 204 amperes. Sorry. So from voltage is equals to current times resistance. So you can be able to get V is equals to 204. That is the current, the armature current, times 40 times 10 raised to power negative 3, which is 8.16 volts. So in order to get the terminal voltage, that is the EMF, not the terminal voltage, will be 200 plus 8.16 plus 20.4, which is equivalent to 228.56 volts. So if you look at that, is the formula for V is equals to IR. That is like you're calculating the voltage drop. You can calculate the voltage drop at the field winding, at the same time at the armature resistance. So if you follow up those calculations, you'll be able to get 228.56 volts. So that is how we do the calculations, and if you follow keenly, at least it should be able to make it easy. Then when you go to the final, current of 5 amperes flows in a winding of an electric motor. The resistance of the winding being 100 ohms determine the applied voltage. It was a direct question from Ohm's law. Current is equals to voltage times current, voltage over current. So if you make voltage the subject and to put in the parameters, because current is 5 amperes, the resistance is 100 ohms, the voltage will be equivalent to 5 times 100, which is 500 volts. So that's just the bit of section A. I just wanted to go through the section A, at least to give a breakthrough of how the questions are. At least an encouragement is just that don't always believe that the unit is very hard. What you just have to do is always read smart, and by reading smart is always look for the key points. You can be able to read a whole book but you get nothing. So always pick zile points zenye ziko relevant. Ukiona kuna notes, zile emphasis vitakuwa naeka a lot of emphasis, those are the correct formulas inafaa uzishike. So if you are looking at the first topic, always look at some few elements about quantities, derived physical quantities. You look at the conversions of formulas, calculating force, energy, power, conductance, resistance, voltage. Those are the key areas that you should look at. When you come to topic 2, you look at how a parallel and a series circuit calculations, how they are done. You also look at the different types of theories. You do some calculations of the theories. When you come to this other topic, you look at the three-phase systems. You look at star connection, delta connections. You look at calculations in single phase, calculations in three-phase. Those are the key points zenye zitakuenable at least to work that extra smart. So you should always unapitia the whole set. Always look at the key points, and after that eventually utapata hizi units zinakuwa very easy. So electrical principles si kitu complex sana, ni kitu yenye unaweza ukiamua tu kuisoma one time, then ni kitu unaweza stick nayo, then ukipitia something through and through, like usisome hard, read na passion. Always be passionate about the unit. Utapata those things will end up being very easy, and utakuwa able to solve a lot of questions afterwards. So I hope this video finds you well, and you'll be able to go through this again and again. It will help you in revisions for any exams as you prepare. Otherwise, I'll also create another tutorial for section B, and hope it will also be helpful to you. Otherwise, have a great time.